Greetings everyone. So in this video I'm going to have a look at geometric progression and application of that. So we've got some machine that costs £90,000, so because I'm in the UK, it depreciates at 10% per year. So how long does it take to get to 5,000? So how many years does it take to get down to £5,000? 10% depreciation here is pretty good. It's better than just about every car you can buy. But anyway, so let's have a look. So we're going to use geometric progression, and the formula we're going to use is going to be this one. Okay, so A is your first term, starting point. R is your common ratio. N is the number of steps it would take, so in this case it's going to be a number of years, but it depends what the application is. It's the number of steps it takes, how many times you apply the common ratio to it. In other words, this is going to be the answer. The N there would be a subscript, which would be your N, because you might be normally, quite often you're working the other way around. We're going to looking for this though, N. As always with these things, the place to start is what do we know? Well, we know that the finishing place, UN, we don't know that N, but the finishing place is 90,000. Okay, the starting point, sorry, I've got that the wrong way around. Duh. So we're going to end at 5,000. Starting point is, A is 90,000, 90k. A common ratio. Now, what is a common ratio? What's 10% as a common ratio? And also, it's depreciating. Now, you might immediately recognise that 10% is equal to, so 10% is equal to 0.1. Okay, like a half is 0.5 and so on. So 0.1, but it's depreciating. So after 1 year, it's only worth 90% of what it was. So it's going to be 90. What's 90% of it each year? So a common ratio R is going to be 0.9. Okay, and then N we do not know. So that's what we're looking for. Question mark over N. So it's quite straightforward. All we've got to do, he says, is put the numbers in. Starting point, always a good starting point. Equals, I've done it again. Equals 90,000 times the common ratio 0.9, and it's to the power of n minus 1, of which we don't know what n is at this stage. So what we're going to do is we're going to get this away from being a power, and we're going to use a very clever but very commonly used method. We're going to use logs because of the log law that says this. So for example, log of x to the power of, let's say, n is identical, 3 lines for an identity, this n log x. So in other words, if we had some numbers in this, let's assume this is log base 10. This works to any log, any base rather. If this was 5 and that was 3, so 5 times 5 times 5, you'd get the same answer both methods. It's an identity. So that's what that means. Let's just leave that over there. Okay. So the first thing that we've got to do though is get this 90,000 away from this so we can apply this log law. So we're going to go like this. Now personally speaking, I would cancel this down. Doesn't make a massive deal of difference when you're using a calculator, but anyway, that's what I would do. It's just neater. 0.9 to n minus 1. So then, if I apply logs to both sides, as I say, any base you wish, I'm going to use, it'll be base 10 in my calculation, but it doesn't matter. So 5 divided by 90 equals So if I do the log law of this, this will come out to the front. I'm going down slope here. 0.9 in there. Sort of almost level. So that equals that. So this has come about because this was a power inside there. So by using that, I've been able to bring it out to the front. We're looking for n. So the next thing to do is move this away by dividing through. So let's make some space for myself, because it's hard work writing down there, I can tell you. So this log divided by that log will equal that. And then if I add the 1 to it, it should, but it will work. So I've now got this log of 5 divided by 90 divided by log of 0.9. If I add the 1 to it, to both sides, to get rid of that, that will equal n. So it's just a case of putting it in your calculator and doing the number crunching. Now by doing that, looking at my answers, I get 27.4. Hopefully that's correct. 27.4 years. Okay, don't know why I've written that in lowercase, because it's not my habit. My handwriting's pretty bad, as you can tell. There's a slight twist in the tail there, in actual fact, and it's not actually 27.4 years, because this method of counting is not how we do accounting. So it's not how we do accountancy, for example, would call that. You'd have to take 1 away, and the reason for that is we don't start counting from 1, we start counting from 0. So if I'm taking steps, this would be 0, that would be my first step, that would be my second step, and so on and so forth. So if I put a number line in, for example, and we've got 0, and then 1, then 2, and then 3, in this case, that's actually where we started. So we need to add 1 on to move it over to there. Sorry, take 1 off rather, should I have said. So take 1 off, and then, so in actual fact, the accounting years would be 26.4. Okay, 0.4 of a year, whatever that may be. Near enough anyway. And that would be it, that would be your final answer. So it's quite straightforward to do in the end. Might look a bit off-putting to begin with, but it's actually fair when you look at this or this, and you're looking for that, you think, how am I going to get that out of there? Remember this method, because it's used a lot and it is extremely useful for solving problems.